All right, thank you again everyone for your patience. We can go ahead and begin today's webinar, Optimize Your Launch. I want to thank you all for taking the time to attend our webinar. We hope you'll find today's 30-minute session helpful in understanding the importance of layout and launch optimization of components when developing high-speed systems. We do want to just go over a bit of housekeeping before we begin. We have all attendees on mute, so please submit your questions via the questions box, and we'll do our best to answer those questions during our Q&A session at the end of the presentation. We've uploaded a PCB launch optimization data sheet that you can download at any time from the handout sections panel of your GoToMeeting and GoToWebinar panel. And at the conclusion of this presentation, you will be asked to take a short survey, and this helps us gather feedback on how to improve future webinars and webinar content. Lastly, we're aware that many of you are taking time from work, so we'll do our best to keep the session for the time allotted. So we do want to go over just our presenters for today. My name is Nat Stevens. I'm the marketing manager here at Ardent Concepts.
And I'm also here. I'm Steve Cristaldi, and I'm the lead applications engineer at Ardent Concepts. Hi, guys.
Thanks, Steve. So before we begin, we do want to review the agenda. So first, we'll look at a company profile. So we wanted to give you guys a snapshot of Ardent Concepts, who we are and what we do. Then we're going to take a look at why do we need optimization. So look at the factors that are causing the need for launch optimization when developing these systems, especially high-speed systems. We'll take some time to review the lessons learned from optimization. So Stephen's going to highlight some lessons learned from improper optimizations or lack of optimization altogether and the ramifications of that. We will then review our Ardent Optimization Services report example. So we'll walk through an example optimization report that Ardent provides its customers to ensure our products integrate seamlessly in your high-speed systems. And at the end, as I mentioned, we'll have a brief question and answer session where we'll take some questions. So a bit about Ardent Concepts. We were established in 2003 and we're headquartered in Hampton, New Hampshire. We're a leading provider of innovative 32 gigabit per second, 70 gigahertz plus interfaces for high-speed electronics. So our core technology is the smallest, fastest, most electrically efficient compression mount connector technology worldwide. As data rate requirements increase and devices and systems shrink, Ardent's products deliver superior signal integrity and a dense footprint that can be reusable across programs to maximize cost savings. Our patented contact technologies are well suited for advanced multi-gigahertz applications such as board stack connectors, coaxial connectors, FPGA sockets, flex circuit connectors, probe interfaces, and mezzanine card connectors. We've got a complete line of high-performance test socket solutions for the most advanced chipsets such as optical engines and components, RF devices, ASICs, switches, processors, and MEMS devices. So Stephen's going to walk you through a little bit about why do we need optimization? What does that mean and why is it important?
Thanks, Nat. Yeah, so, first and foremost, what we're talking about when we're talking about optimizations is we're talking about using ANSYS HFSS or a similar type 3D electromagnetic field solving type program to simulate performance in a transmission line or system. Now, why do we need to optimize, you might ask? Well, first of all, a lot of times when we're dealing with different types of connectors interfacing to a PCB, we need to ensure that we have matched impedance between the connector and the PCB. So we're trying to make sure that we can really well control that transition. Not only do we want to look at that transition between the connector and the PCB, but we want to make sure that we're modifying that transmission or tuning that transmission based on the different types of transmission line format it will go into later, like microstrip or strip line, or even coplanar waveguide. The other thing that we want to look at is how something like a coaxial connector or a coaxial cable that has a cylindrical cross-section changes as it enters into a trace, which has a planar or rectangular signal form factor. Of course, different types of connectors do have different mechanical and electrical properties. So when we're talking about one competitor's or vendor's connector versus another, we need to understand that they all are treated differently, and we need to know how to work with them in order to optimize our systems effectively. And what do we get out of these optimizations? Well, it allows us to look at the S parameters and allows us to tune them to get the best performance of those S parameters. And this is important that we take a look at what's important to us in our systems designs. Insertion loss, return loss, TDR, and this is what optimizations allows us to tune.
So that's a tie-in to this quote we have here, measure twice, cut once. So this adage comes from carpentry, and it rings especially true in board and system design. The idea that it's easier to get it right the first time is essential. I'm sure many of you have been through multiple board spins where you're trying to troubleshoot where failures or losses are happening in the system. And by implementing the correct launches and transitions the first time, you can save time and cost and headache. And so it's important to do so. So for the purpose of today's presentation, what we're really looking at is optimization of multi-coax to PCB transitions. And the goal here is to integrate a high fidelity, high density connector into a high-speed system while minimizing overall system loss. And by doing so, you get all sorts of increased benefits like superior signal integrity, better long-term repeatability. A solderless system like this multi-coax program eliminates signal distortion, quick connection of multiple signals to the PCB, space savings, getting closer to your device under test. You know, the lack of failing of snapping connectors, and it's reusable across programs. So you can slap that footprint symbol down on your next application and reuse that connector.
So in these next couple of slides, we're going to show you some comparative reports that we put together that show what can happen when you have a properly optimized launch transition versus improperly or unoptimized launch transitions. So again, the purpose of this report is to compare these different launch transitions. Again, by optimized, we're talking about using something like ANSYS HFSS or similar 3D modeling software, where we create a model of our transmission line or our system to recreate the real-world system itself. We'll look at the performance of that system, we'll tweak it, and then we'll alter that geometry and measure again to make sure that we end up with the optimized footprint. For these different reports that we're about to show you, we did have some variables that remain the same, and the first of which was the PCB design. So here we're showing you a table of the PCB design that we use to compare these different reports. In general, it's a 3-layer PCB design. We have 1/2 ounce copper plated on the top and bottom layer. Our reference ground is layer 2, and we ran all of these as microstrip cases. We used a Rogers 3003 as our core material. Not only did we maintain the same PCB design and routing configuration, we also had a host of dimensions that remained the same throughout each experiment as well. Now, a lot of these dimensions are the dimensions that you'll find from the standard Ardent TR footprint design PDFs. On the left are the dimensions that remained the same for all experiments. Feel free to look over those, but in general, what remained the same was the ground via orientation, the top layer, anti-pads, and narrow trace gap, and also the PCB trace as it entered into the footprint. On the right, we're looking at the independent variables, and what we changed from experiment to experiment was the capture pad, the reference layer or L2 anti-pad, and the PCB narrow trace, which is the portion of the PCB trace that enters into the TR footprint. Each model configuration was basically the same. Here we show an example. We bring the TR device into the model, and it's shown here by the 10 millimeters of coaxial cable and also the block portion of the TR. Underneath that, we have the PCB configuration, which is based on the following slides we showed you, and we set up our waveports as shown. For the first case, we control the control setup. On the control setup, what we did is we simulated the performance of the TR device with the PCB, and then we tweaked the geometry to obtain the best level of performance. The geometry that we tuned were the independent variables, and you can see, again, those listed in the image on the bottom right. And the resulting geometry, which gave us the best performance, is as follows. We used an L2 anti-pad of 43 mils. We used a top layer capture pad of 18 mils. And the PCB narrow trace was 11 mils. Now, I'd like to call your attention to the consistent dimensions, which are shown on the bottom left. You'll note that the PCB trace for all experiments was 23 mils. And essentially what we're talking about with the PCB narrow trace is that when the PCB trace enters into the TR footprint area, we must neck down the trace. And that's why it becomes 11 mils. This next slide is going to show you the results of that controlled experiment. Again, this is the best optimized footprint launch. This is our control experiment where we tune the geometry to get the best performance. Here we're looking at insertion loss and return loss. The -1 dB point of the insertion loss was around 35 gigahertz, and the -15 dB point for return loss was also around 35 gigahertz. So for this next couple slides, we'll be comparing against this performance. This is our gold standard. Experimental method number 1 setup. Now, what we did with this experiment was we decided to keep the anti-pad on L2 the same, but we made the capture pad a little larger than normal. And the real big thing that we did here is we kept the same PCB trace from outside the footprint, and we ran it right into the capture pad. Now, the reason we did this is because this is something that we commonly hear our customers challenge us on. They say, oh, well, the PCB trace outside the footprint, we can just maintain the same trace width right into the capture pad. In reality, as you can see, the narrow trace must get necked down. Part of the reasoning behind this is due to the flooded ground plane that adds a little bit of capacitance to that narrow trace. The next slide will show you, we'll talk about the performance, or lack thereof, of not optimizing the capture pad and the narrow trace. Here we see again the insertion loss and the return loss. Our -1 dB point of the insertion loss is dramatically reduced from the gold standard of approximately 35 gigahertz to now 12 gigahertz. Almost a third decrease in performance. Our return loss, -15 dB point, goes down to 5 gigahertz. Now this is a seventh of the gold standard, which was around 35 gigahertz. So you can see by not optimizing the capture pad and not optimizing that narrow trace on a simple microstrip experiment, how much the performance can degrade. Our second experimental setup was again something that we see our customers sometimes doing, and that is failure to include the anti-pad on the reference layer. So what we did here is we took our gold standard design with the best capture pad, best PCB narrow trace design, and best anti-pad design, and simply removed the anti-pad. And the results are as follows. Here we can see that insertion loss did not suffer too much. Our -1 dB point only shifted down a few gigahertz. But what we can see was affected more dramatically is the return loss. Now this is an important thing to look at because sometimes designers may only be concerned with one value versus the other. And if you only looked at the insertion loss, for example, you might think, oh, I can exclude an anti-pad from my footprint. Well, that's not true if you're still looking for superior performance in return loss. So it is important to look at all your scattering parameters when you're doing optimizations and ensure that the one that you're looking for, or the one that's most important to you, performance is met. Now at the last, we're going to just compare all the different experiments. We can see here that the insertion loss for the gold standard and for the experiment with no anti-pad remains very similar. And of course, as we've shown before, failure to optimize the capture pad and failure to optimize the narrow trace resulted in poor insertion loss for method number 1. Return loss suffered slightly with the exclusion of the anti-pad, but again, it was the worst when we had too large of a capture pad and had too large of a narrow trace. So in conclusion, what we really wanted to drive home to you guys is that using the ANSYS HFSS or similar 3D field solving software, we want to simulate the realistic performance of our devices and our PCBs and our entire transmission line circuit. When one does not simulate, as was the case with experimental method number 1, it's clear that the insertion loss and return loss can suffer dramatically. And sometimes, as in the case of experiment number 2, some customers may do something that they think is standard fare or that they remember from all their years, like not having an anti-pad on L2. But what we want to drive home to you is that we've done our own research and homework on our own devices here, and we really do know what's best. So when you're working with the TR Multicoax device, you work with us and we work with you to help you understand some things that may not be as intuitive as most might think. These next couple of slides we're going to talk about is actually the Ardent service that we offer, which is footprint optimizations. Now, we have a little bit of information that we request from customers, and as a deliverable, we produce a report. And we're going to go over that process in depth in the next couple slides. So the first piece of literature that we ask for from our customers, or we work with you to fill out, is the TR launch optimization checklist. Now, this checklist contains a number of questions that are designed to help Ardent produce, 1, an accurate quotation for the service, and 2, set up the model in the simulation for the most realistic setup possible. One of the questions I want to point your attention to is question number 3, which asks, how many channels will the TR Multicoax have? Now, this is very important because there is some slight variations in the devices themselves between a single row device and a double row device. What I mean by that is our 8-channel device is 8 channels. 16-channel device is 2 rows of 8. And through that question, we can determine how we're going to best set up the system for you. Also, question is number 7. And that question asks whether the trace design is microstrip or strip line. On the right, we have an exploded view or a blown up view of the standard TR footprint. And we can see that the strip line launch structure is slightly different from the microstrip launch structure. So again, we want to use this checklist to help figure out how to set up the experiment, the simulation, most accurately. The next thing that we ask for is the PCB stack-up. So we'll definitely need this when we go to start work on the project, and the PCB stack-up should contain all the necessary values for us to recreate an accurate PCB in ANSYS HFSS. And with that, we're going to look for the launch layers, the signal layers, those thicknesses, the materials, any plating. We're going to look at the cores, the prepregs, the laminate layers, those thicknesses. We're going to look at the design dielectric values as well. Not only do we want to look at the design dielectric values, but we want to ensure too for high frequency simulations that those values are the high frequency values. Sometimes only low frequency values are available, and that's just not realistic. Other things we'll look at is the via technology. So here in this particular board stack up, there was a drill picture shown on the right, which showed us what the via technology was going to be. And again, this helps us recreate the most accurate printed circuit board that we can for our model and simulation purposes. So we saw this slide before when we talked about the experimental setups, and I just wanted to talk a little bit more about what Ardent does in order to create very accurate simulation models. Now, the thing I'll point your attention to first is the exploded view in the top right. So what we're looking at here is actually a truly deflected spring probe, which is part of our TR assembly. And what we strive to do here is we try to really recreate what that would look like in a real-world situation to get the best performance. The other thing that we like to do here, or something that you guys may be actually questioning, is the use of the TR device itself. Now, some customers have approached us and they've said, hey, you know, I want to simulate your launch structure myself and I don't have your TR model. What can I do? Some of them might try to use an S2P file, and that's just not going to work. You see, the thing is with an S2P file, one of the first questions that comes to mind to me is, how is that S2P file obtained? Where the reference plane is on that S2P file will be integral to how it plays with the rest of the circuit model. In general, however, an S2P file really isn't the best approach for simulating with the TR device, and that's because the TR device itself brings in unique 3D electromagnetic properties to the PCB structure, in which you really need to have the model there, the physical model into the simulation in order to really get those characteristics. It's not just enough to use an S2P file. Now, other people have approached and said, instead of an S2P file, can I just set my wave port at the capture pad? Well, right away, I see a problem with that, because if you look at the microstrip launch, I don't see how you're going to set a wave port there. Usually a wave port's designed as a coaxial structure, and the ground of that coaxial structure would short out right on that narrow trace right there. It is possible to use the wave port in a strip line configuration, and by possible, I mean physically possible, but again, without the TR device there, you're not going to get those properties that that TR device introduces to the board. And some of those properties, you know, in a nutshell, is that the TR body is metallized, and it grounds itself onto the top layer ground plane. So you have some added capacitance from the TR device that you really won't see unless you include it in the model properly. Once we have the model set up and we're running the simulations, on average, we'll run about 10 simulations per configuration. The reason for this is that it takes many minor tweaks to squeeze every drop of performance out of the design. From our starting simulation, we look at the various S parameters in the TDR and make an educated guess on which geometries must be tweaked and in which way. Geometries that we focus on can vary based on the routing configurations. For microstrip, we'll look at the capture pads and anti-pads and narrow trace. And for strip line, we'll look at more of those anti-pads as we go through the via. Above is the result of a final simulation in which we were able to obtain the best performance. We see that insertion loss is very linear to the 40 gigahertz. Return loss is very stable and well controlled to 40 gigahertz. In TDR is showing that the system has well controlled impedance to the 50 ohm characteristic impedance of the transmission line. Once we obtain the best performance, and once we've run our multi-simulations, we'd like to send the customer a simple page highlighting the different geometries that must be changed in order to achieve the guaranteed performance. This is a slide that shows the microstrip design, or a standard microstrip design. The red dimensions are the dimensions that need to be changed. One thing I'd like to point out is that this is not the full design criteria for the TR footprint. We have design files for the TR footprints in a separate document, and this is to be used in conjunction with that. So we have the design files on the website where you can reach out to support or info or your local sales rep, and we'll get you those design files. This is just the only things that need to get changed. So again, it's to be used in conjunction with. Not only do we optimize for microstrip, but we do optimize for strip line. And this next slide will show you some of the critical dimensions that will change for strip line. Again, there's a lot more anti-pads for strip line. And some of the things we look at too for microstrip and strip line is the ground via depth. For the best performance, sometimes we like to stop the ground via depth as the first reference point. Also, the other thing that we supply with the footprint optimization report is this quick summary page. This summary page is actually a copy of the first page of all the footprint design files. This contains the critical rules that are needed in order to lay out a footprint correctly and get your footprint successfully implemented. Some of those things are filled and plated vias, for example. A lot of customers are used to solder down components. Our component is compression mount. It's removable from the board. And because of that, we have to have filled and plated vias because our signal contacts land on the capture pad. So for strip line, if you don't fill and plate a via, the signal can fall directly into the signal via.
All right, perfect. Well, thank you, Stephen, for that summary. Why don't we look a little bit about our motto here, signal integrity is our passion, and how that filters into what we put into our optimization reports.
Thanks, Nat. Yeah, so up until now, we've been showing you guys a lot of simulated performance, but I want to instill confidence in you guys that Ardent, we don't just simulate, we also measure. Here we're showing a quick example of something where we created a perfect model in our program, and then we rapidly created a prototype and took that preliminary measurement, that blue line. Then we made some tweaks. We went back to our model. We tried again, and we're able to then try to get the new measurement to better match that preliminary model. So we're not just simulating here, we're also R&Ding and testing in real time. And some of the tools that we use to do that is our VNAs, our ANSYS HFSS. We have ANSYS Mechanical to truly deflect our contacts. And of course, we have all the necessary calibration and port extension hardware that one might expect to find in any other signal integrity laboratory.
Great. Well, that actually kind of highlights our presentation portion of the webinar today. I did just want to review a brief summary of what was covered today and some takeaways that we thought are key for you all on the line to take away from this presentation today. First and foremost, as signal speeds increase, the need for optimization of system transitions becomes increasingly more important. And we've seen reasons why that's true in some of the cases that Stephen looked at. Anytime PCB stack-up changes, an optimization should be performed. Because of those stack-up changes, it's important to look at how our connector or any connector will work in that system. It's important to increase pressure on PCB vendors for tighter tolerances and stricter manufacturing techniques to prevent issues with the board and to ensure that all the connectors and components on that board work appropriately. Multi-coax connectors offer higher density and fidelity than some of your individual connectors that you may be optimizing the launch of on your boards today. Designers must be aware of routing techniques based on performance requirements, so microstrip versus strip line. And lastly, Ardent has access to advanced measurement hardware, our 67 gigahertz PNA, which Stephen mentioned, and our simulation software, ANSYS HFSS, which makes it easier to eliminate the possibility of system failures being linked to the coaxial components in your system. So with that said, that kind of concludes our presentation area today. We did want to open up for questions and answers in the brief time we have left. We're just a little bit on schedule, if not a little bit over, so we'll take a couple of questions. The first that I see here, and I apologize if we don't get to all your questions, we certainly will follow up with you. The first I see here is, do you charge for this service? A good question off the bat.
Yeah, that's a good question. So we do charge for the service. The service charges vary by complexity. So the easiest thing for us is a pretty much vanilla microstrip, and it goes up with that, usually increasing by the level of strip line iterations that we need to do.
Sure. Thank you, Stephen. Another question we have here, it doesn't look like crosstalk was included in the report. How come?
Yeah, it's a good question. So when we measure our TR devices, we're able to measure the crosstalk at the interface itself. And what we find there is that the crosstalk is at the noise floor of the instrument. So in-house, we have a 67.5 gigahertz PNA, and we took some measurements of crosstalk between the single channels, and we noticed that the isolation was down near the noise floor of the instrument. Later on, we were able to get our hands on a demo unit of a higher frequency VNA, which actually has a lower noise floor, and we repeated the experiment, and we found, of course, that the isolation again went down, so we knew we were reaching the noise floor of our 67.5 gigahertz PNA. For that matter, what this allows us to do for the optimizations is it allows us to only optimize a single channel, understanding that the isolation from channel to channel is basically non-existent on the TR device itself.
Great, thanks, Stephen. Do I need a different optimization for every type of TR device? And then they list out quick latch, right angle, 8-channel, 16-channel.
Yeah, so some of you that might be familiar with our devices or familiar with the website and the product offerings know that with the TR device, we have a multitude of mounting styles as well as a multitude of channel sizes. So what Nat was just listing off was the mounting styles. We have a straight mount that uses screws, and that's actually shown in this image here at the end. We have a quick latch that latches right onto the board with no screws. All the mounting configurations perform identically. So if you have the same PCB stack up and you did optimization for a straight mount, it will work identically with the right angle. The only time you need to do an optimization is if your board stack up changes, or if you're using a different channel size TR device. And even then, it's only limited to single row versus double row channel sizes. So any of the by 4, by 8, or by 12 devices can use the same optimization report and will only need to be changed if it's a by 16 or by 24 channel size.
Great, thanks, Stephen. And we see another question here. Do you also build the boards or just help optimize?
Yeah, this is a good question. Unfortunately, we just help optimize. Our core competencies are really founded in our contact technology and the products around that, such as the TR Multicoax, board-to-board connectors, and integrated circuit sockets. However, we have built a working relationship with a number of high-speed board vendors around the U.S., and we'd be happy to give anyone names if they're looking, so you can contact info or your local sales manager, and we'll have that info for you handy.
Great, thanks, Stephen. Well, it looks like we've taken up the time that we've allotted for today. So if you do have additional questions that we didn't get to answer, we'll certainly follow up with you. We appreciate everyone's time today, and we look forward to speaking with you in the future. Thanks for visiting our webinar, Optimize Your Launch. Have a great day.